This lecture is about inference for linear regression. So we've set up all the background that we need, and we've talked about linear regression, but we talked about it last time as purely as an estimator. What are the mechanics? How do you take the data, and what do you do with it in order to get a coefficient? And then how do you interpret that coefficient? How can you actually use this as an estimator? And now we're going to talk in this lecture about how do you do inference for that. Because the general idea of regression, if you recall, is that you're just using data to guess a function. And for linear regression, that function is going to be a linear function, although we also talked about ways to kind of enhance that with splines and nonlinearities, interactions. But the general idea is that we need to be able to fit these regression functions for many reasons, either descriptive, to just see if there's a pattern in our data, for prediction, to be able to say for a new value of the predictor, what's the outcome before I actually get to observe the outcome. Or in cases where I don't have a label, like if I want to know if this image is a cat or a dog, right? That's actually a kind of a prediction. And for causality as well, to try to understand if I were to change some variable A, what would happen to Y. Okay, now the issue is that we just talked about this in terms of how do you actually get what this prediction function is, this, which as we know is when we're using mean squared error, it can be interpreted as a estimated conditional mean. But if we had a different data set, we would get a different function, right? These data points are not the entire population, they're a sample. And so we want to understand what is the variability of this estimate as a function of the data. So we can imagine, this is our little data generating process here. And we know that it has there's some kind of a true value, or if we had the whole population data set and we did linear regression on the whole population data set, we would get particular coefficients, right? And remember, those coefficients are not indicative of some kind of mechanistic process, because in reality, the outcome is never generated as some linear combination of the predictors. But nonetheless, if you did linear regression on the entire population data, you would get some number, and that would be in some sense the true coefficient, even though it's not real. So a little bit of subtlety there. And then here we have, we generate data sets. We get to see one data set, but we could have seen many, right? These are samples from our population data. And we're sitting over here and we get the coefficients that we get from running regression on this one data set. But we want to understand what are the possible values of coefficients that we could have gotten had we gotten a different sample. And in particular, since we know we don't really care about the coefficients in particular, often, a lot of people do in practice, but it's not the greatest way to look at a regression. It doesn't really target often very specific questions that we should be interested in. So maybe a better way of thinking about this is not, okay, what's the variability of the coefficient, but how does that variability in the coefficient estimates based on the data translate into variability in the ATE that we're estimating, or in an R squared or some other measure of predictive accuracy.